All right, welcome everyone. Oops.
You sure about that?
All right, there we go.
You sure about that? You
Trying
sure about
some
that?
audio stuff here. I put in some filters to try to do some new audio stuff. See if my audio is working.
You sure about that?
All right, there we go.
You sure about that? You
Trying
sure about
some
that?
audio stuff here. I put in some filters. Okay, that sounds good. Okay. So, welcome to this stream, and what I'm trying to tell something different here. One of the things I'm trying is some new audio settings to make my golden radio voice sound a little bit more golden in radio. So I put in a compressor, I put in a noise gate, so you don't hear my slurping noises when I'm sipping on tea, and a little bit of bass boost. So we'll see what that does. The other thing is, so I did a podcast episode. So I have a podcast called The Network Automation Journey. It's just me talking for 5 to 10 minutes about some topic in network automation. And one of the things that I did an episode recently was about SDN, software defined networking. Is it still a thing? Was it ever a thing? What even is SDN? Should we stop using that term? And one of my thoughts on it is that we didn't really have a good definition of it, because like with cloud computing, there was a definition for cloud computing. The NIST, the National Institute of Standards and Technology, came up with a definition. There's 5 things, and we're going to talk about that. 5 things that you have to be a cloud computing platform. And there's a couple different things that they laid out. And initially I thought we didn't have that for software defined networking, but someone on the network automation Slack, I'm sorry, I forget who it was, pointed out there's actually an RFC for what software defined networking is. So we're going to take a look at this. So it's RFC 7426. I did not know this existed until like last week. And I haven't read the whole thing, so I figured I'd read it through here and kind of give some thoughts on that. And before we do that, let's talk about some of the challenges and some of the things we have now. So one of the things, oh man, I freaking hate Copilot. So one of the things, oh, by the way, if you ever have Copilot, this is kind of a thing here. If you ever have Copilot, you can go to Copilot and just disable it, which is what I recommend doing, because it does not help. So is SDN still a thing? There's one thing is the hype train, or the hype cycle. So we're currently eyeball deep in the AI hype cycle. So everything's AI, like refrigerators saying AI or whatever. Like, what does refrigeration have to do with artificial intelligence? But, we've been through, if you've been in the networking or been in the IT industry for a while now, there's certainly a hype cycle that goes on. There was cloud hype cycle. We're trailed off on that. Let's see here. So there was cloud hype cycle. There was the SDN hype cycle. There's been various monitoring hype cycles. But the term, for like the past 30 years, I've heard this is the single pane of glass that's going to solve all your monitoring problems. But of course, it never happens. Now we got, of course, the whole AI hype cycle. There was a sub-hype cycle before AI, because AI has really just pervaded all of knowledge work at this point. But there was a sub-cycle for machine learning in IT, which happened probably about 10 years ago. So there's a couple of products that were trying to solve a bunch of problems with machine learning. Before we had large language models, really. And there was like certain products like Cisco Tetration, which is the absolute worst product I've ever worked with. There's only one product in IT that I refuse to take any jobs on, because they were like, hey, we need you for a contract. It's like a 2-week contract, paid a lot of money. And I'm like, I'm not doing it, because Tetration, there's no positive outcomes with that product. I don't hate everything Cisco does, but it was a machine learning Frankenstein project that never did what it said it was supposed to do. Anyway, so there's a cloud hype cycle. So, but in any hype cycle, there's some truth, and then there's usually a nugget of truth in there. So I'll give you an example with the cloud hype cycle. So there is a cloud hype cycle. But NIST defined cloud computing. I think there was a great, there was a great rant from Larry Ellison, the CEO of Oracle, and he was complaining. I think he was feeling left out because Oracle didn't really have anything, didn't really have a cloud computing story at the time. It was like 2009, and he's freaking out and like, it's just a computer connected to a network. And that was a common lament about cloud computing. And we have kind of the same thing for SDN, software defined networking. So cloud computing was like, how is it any different? It's just a computer and a network and storage. And how is that different than what we have in our on-prem? And NIST defined cloud computing. There were 5 characteristics. One, it had to be multi-tenant. These are not in order. These are just what I remember. So multi-tenant, broadly accessible, which is like APIs, basically. It had to be elastic. It had to be self-service, and it had to be metered. I think those are the right ones. Let's see, NIST cloud computing. Yeah, so NIST came up with a definition of it. And they came up with like 2000, it says 2011, but I think this might have been just a revision. Or maybe not. 2011. Yeah, so on-demand self-service, broad network access, resource pooling, rapid elasticity, and a measured service. So if you don't have those things, you're not a cloud computing platform. Like traditional VMware is not a cloud computing platform. It's not self-service. It's not metered. It's not really multi-tenant. It is pooled resources. But it, because you're having multiple virtual machines share a device, but there's no good separation between them in terms of like being able to self-service and all that. So, AWS, Google Compute, it's all these things. And then there's like OpenStack you can do privately. And there are things you can put onto VMware that will make it these things. But at least we had a clear definition. And this is a very different way of operating. So if you're going to spin up a VM on AWS, it's a very different process than what we've been doing in the 90s and 2000s. And even now, where like you open up a ticket and then someone handcrafts you a virtual machine, goes into VMware, vCenter, creates you a virtual machine, storage, etc. So that's not cloud computing. That's your own infrastructure. And the way it's consumed is very different. So even though it is still computers and network and storage, it's a very different way of operation. And so cloud computing, I think, deserved having its own separate word, a separate term. Now, there was cloud washing, where they just threw cloud on every different product, even though it had nothing to do with any of these things. So that definitely happened. But at least there was a definition where you could say, hey, is this a cloud computing platform? Does it do these 5 things? And if it doesn't, then it's not a cloud computing platform. So I didn't think we had one for SDN. I haven't actually read this or read I read like a first paragraph of it, but I haven't really read this RFC. So what exactly does cloud computing mean? Or what exactly does SDN mean? And let me give you some of my thoughts beforehand. So what is SDN before reading RFC? So what does software-defined networking mean? Geez, I do not want design suggestions. What does software-defined networking mean? So controller-based. Now there's two different types of controllers or at least I think maybe there's more. Just thinking out loud here. Two different types of controllers in networking. There is, well, let's do some diagrams here. There's an approach that really didn't take hold. So there's the SDN controller. And then we had devices. Let me open up another file here. I just need some leaf spine topology. There we go. So we'll group all that. Oh, it's already grouped. Cool. Little tip, if you hold down the shift key, it'll scale symmetrically, or it'll lock the ratios. Because if you don't hit the shift key, you can stretch it out or do that. But usually I want to do that. So I'll just make the font smaller too. Little tip. I think it works for both PowerPoint and Google, the Google equivalent. So we have our SDN controller, and that's the SDN approach. Is my belief is that we run BGP on the controller, and we run, like if we're running the routing protocols, OSPF, and we're running spanning tree. So we're running that all on the SDN controller, and then the configuration that happens could be something like OpenFlow. It's often OpenFlow, but it doesn't have to be. From a theoretical standpoint, the controller is responsible for programming forwarding tables directly. So that's one approach. And then there's what we use today for the most part is the modern network controller. Is we're running the routing protocols. Just stack these all up. And I will group them, shrink them, and reduce the So I don't know if this would be considered SDN. I've not really described this approach as software-defined networking. So we controller sets config state on devices. So this is the different approaches we take. So one approach, we're running all of the routing protocols and layer 2 protocols and so forth on the SDN controller. And then the SDN controller is programming the forwarding tables directly on the devices. So OpenFlow is probably one of the most common ways of doing that. There are some others. And then we have what I call the modern network controller. And all it's doing is setting the configs. So each one of these devices is running its own routing protocols, layer 2 protocols, etc. And we're just setting the config state. And when we talk about any networking device, there's really 3 states that they have. So the three network device states. And this is broadly speaking. So these are generally like layer 2 switches, layer 3 routers, multi-layer switches, etc. So the first state is the config state. So like if you, most of the network devices, layer 2, layer 3, so Juniper, Arista, Cisco, even Cumulus, and a bunch of the other devices are what I would call a single configuration file device. And that might be like running config or startup config, which becomes running config. So the entire configuration state is in one place, one file, somewhere sitting on the file system on the device, and that's the native configuration syntax. So for Cisco, it's the iOS, iOS XR, iOS XE, and XOS. It's running config. Same thing for Arista. For Junos, it's active config or Junos config. I think it's active config. And it's just one thing. So the config state will then start up processes and other machinery mechanisms inside the device, and that will do the operational state. So that's our BGP neighbors, our OSPF or BGP peers, OSPF neighbors, learned VLANs, learned MAC addresses, learned routes. So the operational state will build based on what we set in the config state. So the config state will then begat the operational state. And then the third state is the forwarding state. So for most switches and a lot of routers, this is going to be in some sort of hardware ASIC forwarding engine, like the Broadcom Trident chipsets or the Cisco One chipsets, or Juniper's got their own as well. So that's the RIB or the FIB programmed into forwarding tables. So layer 2, layer 3, maybe even layer 4. So that's the high bandwidth memory, or the TCAM, the CAM, whatever it is, whatever's doing the forwarding. So packet comes into a device, we do some type of lookup on one of the headers, and then we make a decision what to do with that packet or that frame or whatever. So that's informed by the routes that we learned in the routing protocols, or spanning tree, which ports we're blocking, or what VLANs and what MAC addresses we've learned on those VLANs, etc. So they all build on each other. Most modern operations, including automation, is we're just manipulating the config state on each device, and each device is responsible for their own operational state and forwarding state. So most of the time today, modern network automation operates here. We're just manipulating the config state. That's it. That's all we do. And we can do this through a variety of mechanisms. We can use OpenConfig or GNMI or the CLI or an API, netconf, resconf, eAPI, NXAPI, whatever it is. So we're just manipulating the config state. That's all we're doing. And then SDN, to my knowledge, and we'll see if I'm right, because I may not be right. SDN programs the forwarding tables directly. So bypassing a config state and bypassing an operational state. The operational state and config state is then on the controller. So here's another way to look at it. This would be the forwarding state would be down here. Forwarding state. And then the operational state and I think I can make these smaller fonts. So the operational state, so the forwarding state would, with SDN, would be on the devices, of course. So there could be a vSwitch. It doesn't have to be a physical switch or a physical router or whatever. Sometimes it can be virtual. And then we have the config state. That's all on the SDN controller. Whereas over here, all three states are on the device, but we are manipulating the config state on all the devices. So that's the controller approaches. Now, the SDN controller approach is not very common today. We don't see it a lot. There are some exceptions. For example, big switch networks. They had the big cloud fabric and the big monitoring fabric, the BCF and the BMF. And Arista bought them, and that became the converged cloud fabric, the CCF, and the DANS monitoring fabric. So it's and they are still controlled. They're still operated in this manner, this SDN controller manner, and it actually uses OpenFlow to program the forwarding state of each device. Whereas something like even Cisco ACI, and Cisco ACI came out in 2014, and this is Cisco ACI. That's the modern networking controller. So it actually programs the config state of each device. There's a slight difference with ACI though, because in ACI you don't have access to the config state on the devices. Most of the time we do. Most of the time with for example, with Arista, or even Cisco with NXOS, in NXOS mode, our controller is typically something like Ansible and Jinja, or Ansible and something else to manipulate the config state. But it's the config state that sits on each device, the running config. So ACI is a little bit different. ACI, the config state is actually on the monitor. It's on the controller, and then it goes in and kind of the config state on each device is not accessible to you. You cannot go into config mode in ACI on the leaves and spines. So all configuration is done on the network controller. So the ACI is the only one that does that approach. So these are the approaches that I'm aware of, and I think that that's one of the delineating factors between something that's SDN and not SDN is where's the config state, where's the operational state? Is it on the devices or is it on a controller? Another thing is with SDN we have the concept of northbound and southbound protocols. We really don't have that today in modern networking. We really haven't done a ton with, well, at least with the southbound protocols. So let's, so we've got our network devices, and then we have a controller. And we have some sort of protocol for the controller to interact with the devices, to do something with them, forwarding state, config state, whatever. And then there's our workloads. And workloads can be a variety of things. In fact, let's do VMware. Let's do AI. I'm not even going to say AI. Well, I guess I can. So AI or HPC, high performance computing. The needs of AI networking and HPC, high performance computing networking, are very similar, almost identical. In fact, you could probably just say they're identical for the most part. We've got Kubernetes. Let's say kube. So we've got these workloads down here. We had a controller, and then we've got things like orchestrators. And so we have a northbound protocol. So that's a protocol that sits on the controller. And the orchestrators or consumers, users, whatever. So we've got orchestrators, operators. So people, just automation. Orchestrators and automation could probably be the same thing, but I'm just going to leave them separate for now. There's a slight difference between them, or there could be. Let's change that color to yellow. And then there's also a protocol, or potential for protocols. We don't really use it though, where something like OpFlex, Cisco had OpFlex and they were pushing that for a little while. I'd never seen a production use case for OpFlex or a production use of OpFlex. So it's something where like an OpFlex enabled server could communicate with the network and request some resources. Like, hey, I need a VLAN down here, or I need you to extend something. So something like OpenStack might do it, or something like that, OpenShift or something like that could potentially communicate with the network, say, hey, give me a VLAN, and maybe you give some credentials or something like that, and you would be able to do that. I've never really seen that done. I've never seen, there was OpFlex, and I think there was a couple other protocols. So that was one of the ideas in SDN, software-defined networking, is we had the northbound protocol, and it would have to be, the northbound protocol would have to be very similar to the cloud computing. It had to be multi-tenant, API, elastic. I should be able to create network resources and destroy them. It should be self-service. It shouldn't require a network administrator to go in and do this. So we should have credentials. And that was one of the things for multi-tenancy in these network projects, is that if I'm going to do an orchestrator or an automation system and it's not going to be the networking team that does it, I need guardrails, and that's what multi-tenancy does. So as far as I know, ACI was really the only widely deployed controller that was multi-tenant. And that was one of the good things about ACI. EVP and VXLAN can be multi-tenant, but there's no control plane from the vendors that really does that multi-tenancy, where I can say, hey, port 1 and port 1 through 5 is going to be tenant Coke, and port 6 through 10 is going to be tenant Pepsi. And then I'm going to grant these VLANs to Coke and these VLANs to Pepsi. And within those boundaries, you can do whatever you want. So if Coke's orchestrator messes up, or Coke's automation messes up, it's not going to mess up Pepsi, and vice versa. So so they should be they should be multi-tenant. They should have a lot of the characteristics that we would associate with cloud computing. So they should be multi-tenant. They should be API driven. So I should be able to go in through an API versus going in through a GUI. Now, you could have a GUI in a CLI, and those are secondary. It could be it should be elastic. So I should be able to, I shouldn't have to wait for for maintenance window for this to happen. So that's not elastic if you have to wait for a maintenance window for it to happen. It should be self-service, multi-tenant, broadly accessible. It should be metered, so that I can say who consumes how much bandwidth. So maybe I could do chargebacks or charge external customers. So multi-tenant and self-service. And ACI actually is all these things. But the problem was that no one really used it that way. So no one was willing to, we didn't have that many orchestrators or southbound protocol or workloads that could use these southbound protocols. And we had enough change and churn in the network state where any of this stuff made sense. So while ACI is the only one of the modern data center network fabrics that can do these things here, no one cared. No one actually implemented any. Well, not no. You can't really say no one or always or never in networking, because there's always edge cases. But the vast majority of people who are using ACI never used these things. And there's a variety of reasons for that, which we won't go into. So this is my understanding of software-defined networking. So let's take a look and see. Actually, let me see if there's any no comments or anything. If you have any comments or questions, let me know. I put it in the chat room. So let's go through and see. Oh, another thing was, and this was the really early days of software-defined networking. SDN went real wild. So there was going to be like applications. So like some web app. All right. So. And it was going to communicate with the network and reserve resources. So, and these were research projects in some of the computer science departments of these universities back in the aughts. And they were going to have new headers and IP packets. And I would have a consumer of an application. Consumer of app, and like the whole network would be completely application aware. So app aware SDN network, to where a switch or router could make a forwarding decision based off of these other parameters that were going to be added to the headers. That never really happened. Didn't happen outside a lab. I don't think they ever really happened outside of a laboratory. So they were interesting like research projects and stuff, but like there was no way that this was ever going to work. And I was thinking about this on a drive this weekend. So I drove up to, I live in Portland, Oregon, and I drove up to Washington State to do some skydiving, and it's about a 2-hour drive for me to the drop zone. And I was thinking about like from an enterprise networking perspective, if I've got applications on my network, there's only a couple of things I can count on them to be able to do. They can have an IP address, they can have a MAC address, and they can have a default gateway. Beyond that, I can't put any more responsibility on them. They can do an IP address, a gateway, and have a MAC address, and that's it. They can't. It'd be great if they could participate in a routing protocol, because if I could do BGP directly to the endpoints, then I could just, every IP address is a /32, and I don't have to do. I can provide every network everywhere. That'd be great. And the applications are so glued to that virtual machine or that server, they're not portable, so they have to keep their IP address. So there's not a lot we can do. So this was all a pipe dream, and it just never worked out because we would have to change too much of our network. We have to buy new hardware, or the flows wouldn't scale, or whatever it was. So that was real wild, but it never really happened. But if you do like look up SDN on YouTube, you'll see these interesting presentations where they talk about this kind of stuff. And it was like, for example, there was SDN history YouTube. Where's that person? She was software-defined networking. There was a presentation talking about applications. It was pretty wild, and I think it was like about 10, 12 years ago. Wish I had done something like bookmark it or something. That's not it. That's not it. It was a pretty interesting. I can't remember her name. Anyway, so let's go into the RFC. So RFC, it's IETF. They typically handle layer 3 stuff. IEEE typically handles layer 2 stuff. And they have an informational draft on software-defined networking layers and architecture terminology. So just a standardized terminology, so we're all speaking the same language. I don't know that anyone really, I didn't even know this existed until last week, but we'll take a look. So SDN refers to a new approach for network programmability, that is the capacity to initialize, control, change, and manage network behavior dynamically via open interfaces. So just from that sentence right now, that could apply to modern network automation, which is this approach right here. SDN emphasizes the role in software and running networks through the introduction of an abstraction for the data forwarding plane, and by doing so separates it from the control plane. We'll have to see further about this. So the role of software and running networks through introduction of an abstraction for the data forwarding. So like Yang models might be considered an abstraction there. I don't know how important this is. At least, so another thing is I'm taking this from the data center and campus perspective, and there's some other types of networking too. But that's the one these are the ones I'm looking at this through, the lens in which I'm looking at this through. This separation allows for faster innovation cycles at both planes, as experience has already shown. However, there's an increasing confusion of what SDN actually is. Yeah, there's a joke. SDN still does nothing. It was a pure hype train. Everything was SDN. I had 5 lines of Python in a script, and now I've got VC funding, that kind of stuff. But interestingly enough, a lot of the SDN ideas that we had in the late aughts, early 2010s never really happened, or barely happened, or only happened in edge cases. It's like OpenFlow. Other than a few minor products, OpenFlow hasn't been really used, at least in the data center or campus. What layer infrastructure it is in an SDN architecture, and how layers interface with each other. This document, a product of the IETF Software Defined Networking Research Group, addresses these questions and provides a concise, I got some hiccups, a concise reference for the SDN research community based on relevant peer-reviewed literature, the RFC series, and relevant documents by other standards organizations. Okay. This is not a Internet Standards Track specifications to publish for informational purposes. Okay, that's fine. Product of the Internet Research Task Force publishes the results of Internet-related research and development activities. May not be suitable for deployment. That's fine. That's fine. Copyright notice, etc. So this is under fair use. All right, introduction. Software-defined networking is a term of the programmable networks paradigm. In short, SDN refers to the ability of software applications to program individual network devices dynamically and therefore control the behavior of their network as a whole. A couple of names I'm not even going to try to pronounce. Point out that the SDN is a set of techniques used to facilitate the design, delivery, and operation of network services in a deterministic, dynamic, and scalable manner. So that was a very, very broad term. That was more broad than I was expecting, at least for this introduction, because first, software application for network devices dynamically and therefore control the network as a whole. I mean, that's networking. That's kind of if this was the definition of network of SDN, I could just go on a Larry Ellison rant and say it's a network device and you configure it. And you configure it through software as we always have. So that was pretty broad. Let's see if they get more specific. A key element in SDN is the introduction of an abstraction between the traditional forwarding control planes in order to separate them and provide applications with the means necessary to programmatically control the network. Okay, so this might be a good differentiation here. There's a Venn diagram between what is SDN and what is just general network automation. And I think probably one of the biggest ones is that with SDN, applications program the network. Or rather, let's see even more broad. So non-network admins are going to make changes to the network. So this is my network. Could be a data center network, could be a campus network, could be a service provider network, could be something. I mean, this might be a short demonstration or a short presentation here. And then for network automation, or maybe call it net DevOps, network operations, net DevOps. It's only the network admins that are actually doing it. So it's the network admins that are, I mean, technically these are like Ansible is an application, but it's who's operating the applications. Is it like in SDN or in AWS? If you're a consumer of those cloud services, you're manipulating AWS's network, but you're only doing it for your own tenant. And most of the network automation that I've been involved in the past 6 years, so I've been teaching network automation for 6 years now. I mean, it's my primary thing that I've been teaching. It is all network administrators. It is not consumers. So there's the consumers, there's consumers, and then there's the operators. So that might be a big distinction, is who's actually manipulating the network. Is it the consumers of the network or the operators of the network? In network automation, it's just the operators. So a key element of SDN is introduction of an abstraction between the traditional forwarding and control planes in order to separate them and provide applications with the means necessary to programmatically control the network. So you can make an argument that ACI is SDN because it is multi-tenant, and you can set it up so that not the operators can interact with it. So if I'm using Ansible, I'm an operator. Ansible is not multi-tenant. So unless we put a shim layer in between Ansible or whatever, however we're doing the automation of the device configuration state, it's not SDN, at least so far. The goal is to leverage this separation and associated programmability in order to reduce complexity and enable faster innovation of both planes. The historical evolution of research and development area of programmable networks is reviewed in a detail in SDN history, starting with efforts dating back in the 1980s. As documented with, so one thing that kind of bugs me about the networking world is that we are really, really cynical, especially with any kind of buzzword or hype or whatever. And we just think that, we've all been, I think most of us have been burned. For me, it was the network management apps. There were in the aughts, 2000s, there were so many products that came out to be like, oh, we're the one pane of glass, single pane of glass. It's amazing how many single panes of glass there were. But there's a lot of hype and not a lot of substance behind it, and it never really panned out. We still have a really not a great industry there for monitoring. So, are applicable to the latest research and development in SDN and SDN standardization, and have been under extensive investigation and discussion in the research community for quite some time. For example, Rooney et al. Discuss how to allow third-party access to the network without jeopardizing network integrity. That's that multi-tenant I was talking about, is to have non-operators actually impact network forwarding. So if I, like, for example, being given different tenants in OpenStack or OpenShift or whatever, so that they can manipulate their own VLANs without disturbing the other VLANs, etc., without jeopardizing the network integrity, or how to accommodate legacy networking solutions in their new programmable environment. Further, the concept of separating the control and forwarding planes, which is prominent in SDN, has been extensively discussed even prior to 1998. Yeah, I think pretty much it's standard now that we have a different control and forwarding plane. And that's been that way for over 20 years. SDN research often focuses on various aspects of programmability, And we are fundamentally confronted with conflicting points of view regarding exactly what SDN is. Yeah, that's why we're here. One of the things that I think turned out to be, well, something that is important is with programmability is we need a way for a program, that's what programmability is something like an Ansible playbook, Python script, whatever it is, to go into a device and reliably make changes. So ideally that means an API of some type, whether it is an open standard API or a vendor specific API. I don't want to use the word proprietary because it's not like only like Cisco NX API. NX API is proprietary in that it only works on Cisco NXOS devices, but it's not proprietary because Ansible can use it. It's not just Cisco code that can use the API. Anything can use that API. It's based on XML. It's an XML RPC, so it's a well understood method of doing an API. So it's open in that anyone can use it, but it only works on Cisco. So I use the word vendor specific. So same thing with eAPI from Arista. It's a JSON RPC, remote procedure call. So I'm basically I'm encoding CLI commands into JSON or XML. And then we have like the NetMiko library that can go in the standard SSH and interact with the native configuration syntax. There's also netconf. That's what Juniper can use. There's also RESTconf, OpenConfig with Yang models. Most people don't use that for configuration. So there's a lot of programmability. Even if you don't have programmability in your network operating system, there's NetMiko for that kind of thing. So we've made a lot of progress on configuration, manipulating configuration state. For instance, we find that for various reasons, example, work focusing on one domain and therefore not necessarily applicable as is to other domains, certain well-accepted definitions do not correlate well with each other. For example, both OpenFlow and netconf have been characterized as SDN interfaces, but they refer to control plane, control and management, respectively. Yeah. So OpenFlow, it says it refers to the control plane. I would disagree. I think the OpenFlow specification is more data plane. It's programming the forwarding tables of devices. And netconf is the control plane. Absolutely. Yeah, it is the control plane. It's not the management plane. Now, here's another difference here is like, what is the control planes of existence? Stop suggest. I really wish PowerPoint I could just say, just don't give me any. I didn't want it. Stop. I did not want planes of existence. So we have the control plane. So it's routing protocols, static configs, static routes, etc. We have the data plane. Packet frame comes in. What do we do with it? And we have the management plane. And that's typically abstracted control plane. I would say the, control or data plane. It's usually not both. So here, for example, the management plane, these are both management planes. So whether or not we're an SDN controller or a modern network controller, we are the management plane. And the SDN controller manipulates the data plane directly, and the modern network controller configures the control plane directly, and then that affects the forwarding plane. I don't know if that makes sense. Where are we at? SDN research often focuses on varying aspects of programmability. Oh, yeah. This motivates us to consolidate the definitions of SDN in the literature to correlate them with an earlier work in the IETF and the research community. A particular interest is, for example, to determine which layers compromise the SDN architecture and which interfaces and their corresponding attributes are best suited to be used between them. As such, the aim of this document is not to provide to standardize any particular layer or any interface, but rather to provide a concise reference that reflects current approaches regarding the SDN layer architecture. We expect that this document will be useful to the upcoming work in SDN-RG roundtable group, as well as future discussions within the SDN community as a whole. I don't know there's a whole lot of work being done in this anymore. I think, this mode of thinking, I think, is pretty much gone by the wayside. Like I said, we don't see a lot of the SDN controller approach. We're programming the forwarding tables directly. That's really rare. Most of the time the controller is like an Ansible control node is manipulating the config state and not the operational state or the forwarding state. I'll be right back. Okay, I'm back. Just poured myself a beer, and here's the funny thing. So I'll put it up to the camera here. Yep, okay, there we go. So let's see if the camera picks it up. Okay. The Fiber Channel Industry Association. So I did a webinar for them. Here's the funny thing. A while ago, and they gifted me a set of like tumblers, of like fancy drink tumblers with their logo engraved on the side. So thank you very much, Fiber Channel Industry Association. And I poured myself a little bit of beer. I don't normally drink beer. I'm more of a wine person, but when it's really hot out, and it was pretty hot out today, that's what I do. This document approaches the item in the SDN-RG charter titled Survey of SDN Approaches and Taxonomies, fostering better understanding of prominent SDN technologies in a technology impartial and business agnostic manner, but does not constitute a new IETF standard. Is meant as a common base for further discussion. So that's good. I like that they did this. So terminology. Yeah, let's go on this. The document uses the following terms: SDN, a programmable networks approach that supports the separation of control and forwarding planes via standardized interfaces. Resource, a physical or virtual component available within a system. Resources can be very simple or fine-grained, like a port or a queue, or complex, comprised of multiple resources like a network device. A network device that performs one or more networking operations related to packet manipulation and forwarding. This reference model makes no distinction whether a network device is physical or virtual. A device can also be considered as a container for resources that can be a resource in and of itself. Interface, a point of interaction between two entities, so not a networking interface. When the entities are placed in different locations, the interface is usually implemented through a network protocol. If the entities are co-located in the same physical location, the interface can be implemented using a software application programming interface, API, interprocess communication, or a network protocol. Application. I'm curious about this. So an application in the context of SDN is a piece of software that utilizes underlying services to perform a function. Application operation can be parameterized For example, by passing certain arguments at call time, but it is meant to be a standalone piece of software. An app does not offer any interfaces to other applications or services. A service, a piece of software that performs one or more functions and provides one or more APIs to applications or other services of the same or different layers to make use of a said functions and returns one or more results. Services can be combined with other services or called in a certain serialized manner to create a new service. So application. An application in the context in a piece of software that utilizes underlying service to perform a function. So I don't know if that means like Ansible as an application or like my my web app. Forwarding plane, the collection of resources across all network devices responsible for forwarding traffic. Operational plane, the collection of network resources responsible for managing the overall operation of individual network devices. Control plane, a collection of functions responsible for controlling one or more network devices. Control plane instructs network devices with respects to how to process and forward packets. The control plane interacts primarily with the forwarding plane and to a lesser extent, the operational plane. The management plane, the collection of functions responsible for monitoring, configuring, and maintaining one or more network devices as part of network devices or parts of network devices. The management plane is most related to the operational plane. Application plane, the collection of applications and services that program network behavior. All right, so I'm not real wild about these definitions. Especially forwarding plane, operational plane, and control plane. I don't like these definitions personally. I would say the forwarding plane, the collection of resources across all network devices responsible for forwarding traffic. I agree with that one. Yes. The control plane, the collection of functions responsible for controlling one or more network devices. The CP instructs network devices with respect to how to process and forward packets. The control plane interacts primarily with the forwarding plane. I would agree with that as well. And to a lesser extent with the operational plane. That and the definition of the operational plane, the collection of resources responsible for managing the overall operation of individual network devices. So that might be like the network operating system. Or APIs or something. I just don't like this. It's too vague for me in the management plane. Yeah, I think, in my opinion, for whatever it's worth, the operational plane and the management plane are not really well defined, at least in my head. Maybe there's something I'm missing and I'm not getting it. Device and resource abstraction layer. The device is resource abstraction layer based on one or more models. If it is a physical device, it may be referred to as the hardware abstraction layer. The DAL refers to a uniform point of reference for the device's forwarding and operational plane resources. Now, here's another thing. Well, let's go on. Device and resource abstraction layer. So there's several layers of abstraction in most networking devices. So we have the forwarding engine. So this is forwarding engine. Let's say hardware or software. So the forwarding engine might be like the Broadcom Trident chip, something like that. And then we have the NOS, Network Operating System. And the NOS is going to have several ways to interact with it typically. So the one we're most familiar with as networking people is going to be the CLI. But it also probably has API. And you can go in, or let's say netconf. Actually, put in another layer here. So there is the native configuration syntax. So is that the management plane or is that the control plane? I don't know. Let's bring these to front. So we got netconf, we got restconf. There's openconfig, or also known as GNMI. There's vendor-specific APIs. Let's group these together and make them bigger. So in each of these programs, the other layer. So the network configuration syntax interacts with the network operating system, and then the network operating system builds the forwarding tables and then programs the forwarding tables or whatever forwarding mechanism is going on. And then we can go into the CLI, the netconf, restconf, something like that, openconfig, GNMI. You can even do, like, some devices will let you even make config changes via SNMP. So where does the operational plane and management plane fit into this? So this is just about every network device out there. Now, not all of them support every method of configuration. About all of them, so Cisco, Arista, Juniper, Nokia, Huawei, Avaya, HP, etc., they have a CLI. There's some sort of CLI. A lot of times it's very Cisco-like. We call it the industry standard CLI. But sometimes it's something very different, like Nokia and Juniper have a very different configuration syntax. And sometimes they have multiple configuration syntax. Like in Junos, you can use the native configuration syntax, which is kind of Yang-ish, but it predates Yang. Or you can use the set commands. Or you can use netconf. But there is a native configuration syntax. And for like Juniper, like, it looks something like this. So there's a juniper.conf. And it looks like, nope. Yeah. Anyway, it's a specific syntax that sits on the network operating system, which then will program in the forwarding tables. Or maybe if it's software based, it's the software and the forwarding tables are the same thing. So. And so also, what's the device abstraction layer? Like openconfig, it's an open API, or even netconf. They are abstracting the forwarding engine, the forwarding plane. So is that a hardware abstraction layer, or is there something like the fib on the network operating system needs to get programmed into the forwarding table? So there's an SDK to program in the Broadcom chips, etc. So I don't really know here. So management abstraction layer provides the access to the management plane southbound interface. So the southbound interface, I'm thinking here they mean like OpenFlow. So there's a network services abstraction layer, provides service abstractions that can be used by application and services. So this I would say would be the multi-tenant API controller. So that seems pretty straightforward. Oh, good. They got a diagram here. Okay, so let's take a look at this diagram. So we get an application service. So this would be like maybe Kubernetes or maybe OpenStack or OpenShift or even VMware with vCenter and some other stuff interacting with the network abstraction layer. So this would be the multi-tenant, API driven, and then it would go to a control plane and management plane, service app, service, control abstraction layer management. Yeah, this I'm not getting here. So a CP, control plane, southbound interface, management plane, southbound interface. Yeah, like we just don't do it this way. I don't recognize anything that I've seen in modern networking in the last 10 years here. Maybe it's one or the other. Maybe it's declarative versus imperative. I don't know. The device and resource abstraction layer for the networking device would be the forwarding plane and operational plane. Maybe this is like open config and maybe this is open flow. So maybe that's what they mean. We'll see. So this document follows network device-centric approach. Control mostly refers to the device packet handling capability, while management typically refers to the aspects of overall device operation. We view a network device as a complex resource that contains and is part of multiple resources similar to DIOPR. I don't know what that is. Designing interfaces for open programmable routers. Resources can be simple, single components of a network device. For example, a port queue of the device can also be aggregated resources, etc. The reader should keep in mind that we make no distinction between physical and virtual resources. Okay, that makes sense. I agree with that. SDN spans multiple planes as illustrated in figure 1. So this is figure 1. Starting from the bottom part of the figure and moving towards the upper part, we identify the following planes. The forwarding plane, responsible for handling packets in the data path based on the instructions received from the control plane. So that would be what I described as the operational state and the forwarding state. Actions of the forwarding plane include, but are not limited to, forwarding, dropping, and changing packets. The forwarding plane is usually the termination point for control plane services and applications. The forwarding plane can contain forwarding resources such as classifiers. The forwarding plane also is widely referred to as the data plane or data path. Yeah, okay, that's right. I track with that. Operational plane, responsible for managing the operational state of the network device. Whether the device is active or inactive, the number of ports available, the status of each port. The operational plane is usually the termination point for management plane services and applications. The operational plane relates to network device resources such as ports, memory, and so on. So maybe this is the config state. We note that some participants of the IETF, SDN, RG have a different opinion on what the definition of an operational plane is. That is, one can argue that this operational plane does not contain a plane, constitute a plane per se, but it is in practice an amalgamation of functions on the forwarding plane. For others, however, the plane allows one to distinguish between different areas of operation. Therefore, the operational plane is included in the plane figure 1. Okay. Control plane, responsible for making decisions on how packets should be forwarded by one or more network devices and pushing such decisions down to the network devices for execution. The control plane usually focuses mostly on the forwarding plane and less the operational plane of a device. The control plane may be interested in operational plane information, which could, for instance, the current state of a particular port or its capabilities. The control plane's job is to fine-tune the forwarding tables that reside in the forwarding plane based on the network topology or external service devices. I think this is a little overly broad. I think we could just say the routing protocols and the config state. Management plane, responsible for monitoring, configuring, and maintaining network devices. For example, making decisions regarding the state of a networking device. The management plane usually focuses mostly on the operational plane of the device and less the forwarding plane. The management plane may be used to configure the forwarding plane, but does so infrequently, and through a more wholesale approach to the control plane. For instance, the management plane may set up all or part of the forwarding rules at once, although such action may be expected to be taken sparingly. Yeah, I'm not really liking the definitions here. In that I don't see how we do things in the modern network represented here. All right, application plane. The plane or application services that are defined. Okay. The plane where applications and services that are defined network behavior reside. Applications that are directly support the operation of the forwarding plane are not considered part of this application plane. Note that the applications may be implemented in a modular and distributed fashion and therefore can often span multiple planes. Yeah, I'm not real sure what that means. RFC 7276 has defined the data control and management planes in terms of operations, administration, and maintenance. That might be something I need to take a look at later. Maybe that'll give me some more insight. But right now, I like this separation a lot better, because I don't really see this. I can look at a modern network and see, okay, this is config state, operational state, and forwarding state. Here, I'm not sure where the separation between all this stuff is. Maybe I'll get it later. All planes are mentioned above are connected via interfaces. An interface may take multiple roles depending on whether or not the connected planes reside in the same device. If the respective planes are designed so that they do not have to reside in the same device, then the interface can only take the form of a protocol. If the planes are co-located in the same device, then the interface could be implemented via an open proprietary protocol or open proprietary software inter-process communication API or operating system kernel system calls. For example, software programs that perform specific computations that consume services without providing access to other applications can be implemented natively inside of a plane or can span multiple planes. For instance, applications or services that span both the control and management plane, and thus be able to use both control plane southbound interface and management plane southbound interface, although this is implicitly illustrated. Would be OpenFlow and OFConfig. It's OpenFlow and OpenConfig. Or OpenFlow Management and Configuration Protocol. Huh. I didn't know this thing existed. What is this? Is this OpenConfig? It's not even there anymore. Okay. Yeah, a lot of this stuff got dropped. Like I said, OpenFlow is kind of a dead protocol. It's used in a few places, but I don't think it's going to go anywhere. I don't think that's going to be where we do stuff. Let's speed things up. Yeah, I'm not sure I would like all these abstractions. Network devices. Network device is an entity that receives packets on its ports and performs one function. I think we know what that is. Control plane. Control plane is usually distributed and is responsible mainly for the configuration of the forwarding plane using a control plane southbound interface. I don't agree with that. Communication between control plane entities, colloquially referred to as east-west interfaces, usually implemented through gateway protocols such as BGP, and other protocols such as path computation element and communicate. I don't even know what those are. These corresponding protocol messages are usually exchanged in-band and subsequently redirected by the forwarding plane to the control plane for further processing. I don't. It's not something I see. The control plane protocols, these are, I just don't like this. I don't know if this is just because I've been doing things another way, or if there's something to this that I'm just not grepping, I'm not grokking, I'm not understanding. But even if my what I know about SDN, or what I thought I knew about SDN, doesn't really do with any of this stuff. Management plane is usually centralized and aims to ensure that the network as a whole is running optimally by communicating with the networking operational plane using a management plane southbound interface. Management plane functionalities are typically initiated based on overall network view, traditionally have been human-centric. However, lately algorithms are replacing most human intervention. Fault monitoring management, configuration management. Yeah, I'm just not seeing this. Let's speed things up a little bit. Discussion of control management planes. The definition of a clear distinction between control and management in the context of SDN received significant community attention during the preparation of this document. We observed that the role of the management plane has been earlier largely ignored or specified as out of scope for the SDN ecosystem. In the remainder of the subsection, we summarize the wrong emphasis on the wrong syllable. We summarize the characteristics that differentiate the two planes in order to have a clear understanding of the mechanics, capabilities, and needs of each respective interface. Timescale. A point has been raised regarding the reference timescales for the control and management planes, regarding how fast the respective planes are required to react or how fast it needs to be manipulated, the forwarding or operational plane of the device. In general, the control plane needs to send updates often, which translates roughly to in the range of milliseconds that requires high bandwidth and low latency links. In contrast, the management plane generally reacts at longer time frames, minutes, hours, or even days. Thus, wire efficiency is not always a critical concern. A good example of this is the case of changing the configuration state of a device. That is one good way to differentiate. Routing protocols are they're updating very often. Persistence. Another distinction between control and management planes relates to state persistence. A state is considered ephemeral if it has a very limited lifespan. It is not deemed necessary to be stored in the non-volatile memory. A good example is determining routing, which is usually associated with the control plane. On the other hand, a persistent state has an extended lifespan and may range from hours to days or even months, and is meant to be used beyond the lifetime of the process that created it, and thus used across multiple reboots. That's pretty. So operational state is ephemeral. Config state is more persistent, because that's going to be running config, then saved as startup config. Locality. As mentioned earlier, traditionally the control plane has been executed locally on the network device and is distributed in nature, whilst the management plane is usually executed in a centralized manner remotely from the device. However, with the advent of SDN centralization or centralizing or logical centralizing, the controller tends to muddle the distinction of the control and management plane based on locality. Okay, so I think I get this. The SDN approach, like I talked about, is the the control plane has been executed locally, and the management plane is off the device, and so that's what this is. Modern network device controllers is. This would be the management plane here, and then we're configuring the configuration state on the devices. Versus the SDN controller, which tends to muddle the distinction between the control and management plane based on locality. I don't even know if I agree with that. Because what they're calling a control plane, I would call the operational state. So that's the routing protocols, the peers, the neighbors, the stuff that's ephemeral. It's changing from moment to moment depending on what the routing protocols say. And then we have the forwarding state. So that would be what's programmed by like OpenFlow. Okay, CAP theorem. What is CAP theorem? CAP theorem views a distributed computing system as composed of multiple computational resources, CPU, memory, storage, that are connected via communications network and together perform a task. The theorem, or conjecture by some, identifies three characteristics of distributed systems that are universally desirable. Consistency, meaning that the system responds identically to a query no matter what node receives the request. Availability, and partition tolerance. Forwarding a packet through a network correctly is a computational problem. One of the major abstractions that SDN posits is that all network elements are computational resources that perform the simple computational task of inspecting fields of an incoming packet and deciding how to forward it. Since the task of forwarding a packet for network ingress to the network egress is obviously carried out by a large number of forwarding elements, the network of forwarding devices is a distributed computational system. Hence, the CAP theorem applies to forwarding packets. Yeah, but do we care? I don't care. In the context of CAP theorem, if one considers partition tolerance of paramount importance, traditional control plane operations are usually local and fast, while management plane operations are usually centralized and maybe slow. The CAP theorem also provides insights into SDN architectures. For example, a centralized SDN controller acts as a consistent global database, and specific SDN mechanisms ensure that a packet entering the network is handled consistently by all SDN switches. The issue of tolerance to loss of connectivity to the controller is not addressed by the basic SDN model. When the SDN switch cannot reach the controller, the flow will be unavailable until the connection was restored. Oh, that is bad. All right, that is a yeah, I forgot about that. Yeah, if your controller goes offline, you are hosed. I think that might be one of the reasons why this model of the SDN controller never really took off. And we use this model too, because this is a true distributed system. This is very much less distributed because the SDN controller is responsible for running the routing protocols to build its view of the network, whereas modern network automation is we're just pushing config state. We're not pushing forwarding state, we're just pushing config state, which will then spin up the routing protocols and the layer 2 protocols, and each device is responsible for its own little domain of figuring out what the network is. So the SDN controller, if we lose this interface, what happens here? Well, what happens here is we lose all of, because the SDN controller, it's probably in-band doing like BGP. So then we lose BGP connectivity to the device. We can lose that session. Also, one of the big, this is another thing here. So forwarding state versus config state management. So like I said, one of the biggest things with the SDN controller, it configures the forwarding state. At least so far, everything I've read kind of says this. And a network automation is the config state. So one of the biggest things is that with this approach, first packet in a flow goes to controller. Controller never sees data plane. So, for example, the converged cloud fabric or the big switch network, big switch fabric, or the big switch, what they call it, the big fabric, whatever big switch's network was, the first packet had to go to the controller in a given flow because the controller would then have to figure out what to do with it. It would take that information and then set it off the devices. That packet never went back to the data plane. So you always lost one packet with the SDN controller in the beginning of a flow. But with network automation, you never have to do that. And I realized that if we lose this interface, then we've lost the network. So that's very, very bad. Whereas if we lose the controller here, every device still has its config state. It'll keep forwarding based off whatever config state was last issued. Even if you reboot them, it'll still forward exactly like it did before. So that might be one of the biggest reasons why this never worked out. So network services abstraction layer provides access from services of control management application planes in order. We note that the term SAL is overloaded and is often used in several contexts, ranging from system to... Yeah, that's one of the problems of all of this, is that like a lot of these terms mean different things to different people. Management plane and management control data and forwarding plane, they're all like different things to different people sometimes. Service interfaces can take many forms pertaining to their specific requirements. Examples of service interfaces include, but are not limited to, RESTful APIs, open protocols such as netconf, interprocess communications, Cobra interfaces. I don't even know what that is. Sounds like I should know what that is. I have no idea what that is. Service interfaces can take many forms pertaining to their specific requirements. The two leading approaches for service interactions are RESTful interfaces and RPCs. Yes, I do agree with that. Both follow client-server architecture and use XML or JSON to pass messages, but each has some slightly different characteristics. RESTful interfaces designed according to the representational state transfer design paradigm, REST, have the following characteristics. Resource identification. Individual resources are identified using a resource identifier, for example, a URI. We call that the noun. Manipulation of resources through representations. Resources are represented in a format like JSON, XML, or HTML. Self-descriptive messages. Each message has enough information to describe how the message is to be processed. Hypermedia has the engine of application state. A client needs no prior knowledge of how to interact with the server, as the API is not fixed but dynamically provided by the server. And these aren't really useful distinctions for me. RPCs, XML, RPC, and the like have the following characteristics. Individual procedures are identified using an identifier. A client needs to know the procedure name and associated parameters. I feel like there's just a way better way to explain this between a REST API and an RPC. So let me just throw together some. Maybe I'll use this for another presentation because I think probably a good idea here. Turning into an old man, shaking my fists at RFCs. So I think I have a better idea.
You sure about that? You sure about that? You sure about that?
But you know, I like helping people out.
And who loves you? And who do you love?
That's gonna get real annoying. I'm gonna guess. So let's talk about REST API and RPCs. So REST API, we typically call it's a CRUD style interface. So that's create an object, read an object, update an object, delete an object. So create, read, update, delete. We use a noun and a verb. A noun is a URI. Ships NCC 1701. Crew manifest. And then a verb. And then verb is either post, update, post or put, update, delete, or get. Change that color. And REST APIs are good for object-based controllers. So in the networking world, we have two different types of devices. So over here is what we're this is what we're normally used to. This is the single configuration file device. So these are your routers and your switches from Cisco, Arista, Juniper. So we got a router, and we got a switch. And it's a single configuration file. So running config, active config, whatever it is. And then we have the controller based. So this is something like Cisco ACI. With a controller-based system, you're not directly interacting with the config state of a device. You manipulate the controller. The controller will then, on your behalf, will manipulate the device. For example, all wireless systems. Because think about it, there's like, I don't know how many, if you've got a big building, I don't know how many access points you've got, but it could be in the hundreds or even thousands or even tens of thousands throughout your enterprise. You're not going to go into each one of those devices and do a config T. You're going to go into the controller. The controller will then push to the devices. So I'll put these up here. So the controller will sit between and you won't have direct access to configure the configuration state of these devices. So like I said, that's Cisco ACI is like that, and just about every wireless access system. So probably one of the most common, if not the most common, controller-based system. So there's single configuration devices, and copy these, and then they all have like some sort of running config or equivalent, because they're not all Cisco devices or eAPI devices. Just a single config file. That's it. That's their configuration state. Now, for the single configuration device, usually we have an RPC API. And the RPC API is best for manipulating these single configuration files, typically. And then for the controller-based device is a REST API. Because that is abstracting away the direct communication. So another way to think of it is an RPC is declarative. We're telling it exactly what to do. So an RPC is typically a remote procedure call. We're encapsulating the actual CLI syntax in most cases into either JSON or XML, and then pushing that to the device. The device will unpack that XML or JSON and then run that command, a remote procedure call, a remote command call. Whereas the REST API is interacting with these abstracted objects of like an access point group or a switch group or a interface policy group or something like that. So that's what the big difference between the two is. An RPC is basically just raw CLI syntax. For example, eAPI from Arista is basically, it's just EOS commands encapsulated into JSON. That's it. That's exactly what it does. Application plane. SDN model view, we advocate that the SDN southbound interface should encompass both CSPI and MSPI. So that's SDN controllers such as Knox and Beacon are a collection of control plane applications, control plane and management plane southbound interfaces. Yeah, we just don't do any of this. I don't even know what Knox or Beacon is. Are they even still around? Yeah, I don't know. I've honestly never even heard of those two. So this document's old, so it's 10 years old. So these two might they're still around, like Knox controller. Developed by Nicira. Knox was donated to the research community and became a foundational tool. $13 years ago, so I don't think it's really been used. I don't know if this is the Knox repo. Yeah, it doesn't look like it's very active. And Beacon, I've never heard of that one either. Beacon open flow controllers, that's still around. Oh, maybe it was OpenFlow, or Big Switch rather. Beacon is a Java-based OpenFlow controller? Ooh. That is rough. Like Java or JavaScript? Well, that's not around either. Okay, so neither of these, there's a reason why I haven't heard of them, because they're not around anymore. But I never heard of them even in the height of all this stuff. The IETF forwarding control element separation forces. IETF forwarding control element separation framework consists of one model and two protocols. Forces separates the forwarding plane from the control plane via an open interface, namely the Forces protocol, which operates on entities of the forwarding plane that have been modeled using the Forces. I've never heard of any of this stuff. I mean, I'm not like super dialed into everything, but I'm not living under a rock. Logical functional blocks. I don't think any of this ever got used other than research project. Oh, NetConf and Yang. I know about this stuff. I have opinions on NetConf and Yang. Yeah, so Forces does not do anything. NetConf and Yang is. My view, here's my quick opinion on Yang. As a data modeling language, it is great for pulling resources from a device for telemetry to know what stuff is going on. Click that out. It's great for knowing what stuff is going on. It is terrible for configuration. Absolutely abysmal for configuring devices. There are so many other better ways. So I don't like Yang for configuring devices. OpenFlow. OpenFlow is a framework originally developed at Stanford and currently under active standards development. I don't think it is anymore. Initially, the goal was to provide a way for researchers to run an experimental protocols and production network. Yeah, that's not bad. I don't think so. OpenFlow, is it still a thing? Yeah. Not really a thing anymore. Introduction to the Internet Routing System provides a standard interface for a routing system or real-time event-driven whatever. Essentially, one of the goals of I2RS is to make the routing information base programmable, thus enabling... I don't think I've ever seen this before. G-Ribby, maybe? Oh, SNMP. Oh, a love-hate relationship with SNMP. SNMP is great only because it's everywhere. It's not a reliable way to make configuration changes. I don't think most vendors support config changes. There have been some. I remember Radware back in the 90s had a Java-based GUI, and its backend used SNMP version 3 to make configuration changes on the Radware load balancers. And I think that's the only device I knew that was solely configured by SNMP. Well, not solely, but you could do everything via SNMP. Most devices you can't do everything, and a lot of devices you can't do anything set-wise via SNMP. It's only get. PCEP, Path Computation Element Architecture, PCE. I didn't even know about this until last week. I think some people I knew have tried it. BFD, that's great. We use that. I don't know why that's related to this, because it's just a way to detect failure of a routing protocol or a link pretty quickly. And the rest of this, okay, this, all right. So we're done with the document. We're about an hour and a half into it. This raised more questions than it answered. It didn't really clear anything up for me. It certainly doesn't describe the network that I know, and it never described any network that I ever knew. This kind of stuff does. So maybe I'll do a presentation based off this. I'll do a quick video off of this, but what I learned is that the definition of control plane, management plane, forwarding plane really didn't click with me, at least. And that may be just a limitation on my own. Yeah, so forwarding plane, operational plane, control plane, management plane, and application plane. They were not delineated to my satisfaction. And yeah, this didn't help what SDN is. So some of the stuff we do use, some of the stuff is what we use today. I think the overall vision of SDN has been abandoned. This doesn't really define it the same way that NIST defined cloud computing. NIST also defined public versus private cloud, and also the X as a service. So infrastructure as a service, software as a service. They just did a much better job, in my opinion, NIST, of defining what cloud computing was. Like, I thought it was a very solid definition. This didn't really help me. And maybe it's because I'm dumb. But this did not clear anything up for me. It did not build a vision of how they wanted computing to networking to happen. Or any of this stuff that you're seeing on the screen here. So I'm a little crankety about this. I'm a little salty. I was hoping for some more clarification. I did not get it. So, all right. So, any questions or comments you want to put in the chat room? I will answer them. But I think I'm going to wrap this up here and go get myself another glass of beer. Well, that did not help. Okay. My opinion on SDN hasn't changed. I don't think we should use the term anymore, because I don't think what the vision of SDN was is what we're doing now and what we're moving towards. I think some of it overlaps a little bit. I think I think the Venn diagram. I love Venn diagrams. So this is SDN. And this is what I would call modern network operations, specifically network automation. There are overlapping parts. But yeah, there are overlapping parts between them, and I don't think, though, that we should be using the term anymore, because it just doesn't. Yeah, it just doesn't describe what we do, and this document didn't help. So, thank you for watching, and I'll see you on the next stream.